fast X-ray transients, which is my main research topic. Okay, in the last decades, our knowledge about transients in general improves in order of time scales, in order of energies. We know a lot about different kinds of transients, from radio bands like fast X-ray transients to the gamma rays with the gamma ray bursts, and in between we understand better supernovae, optical, near infrared, and all the electromagnetic spectrum. However, in the case of X-rays, and particularly soft X-rays, between 0.3 and 10 kiloelectron volts, we don't understand really well the time domain and the variability in the X-ray scale. So in the X-ray transients, we are related with different kind of astronomical objects, from stars to AGNs, and we're covering a large scale in time and also in luminosity. In here, you have a plot. In the x-axis, you can see the time scales in seconds, and in the y-axis, we have the X-ray luminosity. And in here, the different boxes, the color boxes, are related with different kind of X-ray transients, so from flare stars, novae, to gamma ray bursts that you can see here, for instance. So we are particularly interested in a kind of transient that we call extragalactic fast X-ray transients, that we mark in here with this blue box. And this blue box covers a different kind of extragalactic object that we understand more or less, like gamma ray bursts, supernova shock breakouts, and tidal diffusion events involving intermassive black holes and white dwarfs. So I will explain a little bit about the possible sources that are related with this class of extragalactic fast X-ray transients. The first one are the SBOs. SBOs, shock breakout, are related with Corculum supernovae, and we expect that when a massive star start to collapse, eventually a shock breakout is produced and start to travel inside the stellar medium, and when this shock reaches the surface of the star, we can detect a flash of X-rays in the soft band that is related with the collapse of massive star. So in here we have the typical SBOs that we can expect in the X-ray band. Until now, unfortunately, we detected just one SBOs robustly. This event was called Supernova 2080 and was detected serendipitously, while Swift was observed other supernovae, the supernova 2007 UY, that it's in here. This is an XRT image. This is the location of this the supernova that was observed initially, 2007 UY, and randomly appeared this other supernovae 2080. And here you have the location in an optical imaging of the source in the outskirts of this galaxy. Subsequent observation in optical and UV and near infrared suggests that this SBOs was related with a supernovae emission, type 1 BC, and is the only fast X-ray transient that we identified an optical near infrared counterpart until now. So this is one of the possible channels related with fast X-ray transient, extragalactic fast X-ray transients. The other one is related with tidal diffusion events, but a particular kind of tidal diffusion events involving a white dwarf at an intermassive black hole. That means mass between 10 to the 3, 10 to the 5 solar masses, more or less. So we expect that the X-ray emission of these kind of sources are related with the tidal diffusion of these compact objects, compact stars, and the accretion that is formed after once the star is disrupted. So until now, we have identified just a couple of candidates to this kind of tidal distribution events that you have in here, Joker et al. 2013 and Blaney et al. 2018, and we expect some luminosities in X-rays higher than 10 to the 49 x per second for this kind of objects. So it's one of the possible channels that could be explained high energy fast X-ray transits. The other one is related with binary neutron stars. So we know that when we have a binary system of neutron stars, they eventually could be merged, and the merge of these two compact objects will reproduce the gamma reports that we understand particularly really well. However, when these two neutron stars merge, we have two different kinds of remnants, a black hole or a neutron star, a proto-magnetar. And this possible remnants depends on different parameters previous to the merger. But in the case that we have like a remnant, a massive star, we expect that this massive, proto-magnetar with a masses in the order of 2 solar masses could be emit X-rays in the way like magnetar nebula emission. Until now, we have some possible candidates related with this magnetar emission produced by the merger of two neutron stars that you have in here, different papers. And one of them in here, you can see the light year of this event that I will explain a little bit in the next slides. And the last one, a scenario that could be extragalactic fast X-ray transients are related with off-axis GRB. So we expect that eventually long GRBs, low luminous GRBs could be produced X-ray flashes related with a cocoon emission, or maybe a frustrated jet GRB. So we expect that eventually, in the case of the emission is related with a cocoon emission, we can expect an afterglow like you can see here in these light years that could be mimic the shape of the light years related with fast X-ray transients. So these 4 different channels eventually could be explained some of the features that we expect for fast X-ray transients, timing and spectrum. A little bit about the history related with extragalactic fast X-ray transients. I split the history into phases, pre-2000s and after 2000s, when we have the new generation of X-ray missions. So previous this new generation of X-ray satellites, we have these satellites like you have in here, Ariel 5, Rosat, Einstein, and in the literature we identified that several fast X-ray transients was identified. Around 150, more than 150 fast X-ray transients were detected in archive data of these events. However, the features of these satellites was not possible to analyze in detail the nature of these transients. They had poor localization, for instance, so was not possible to identify the host galaxy of these transients. And other, if you can see in this plot the position of these transients in the galactic coordinates, you can see that you have a distribution in the sky that some of these events are inside the galactic plane, which suggests that eventually not all the events that you have in here are related with an extragalactic origin. Maybe an important fraction of them are related with flares, stellar flares, essentially. So we are not sure if the transients that was identified in these missions are really associated with extragalactic objects. So just a couple of them, some of them in the order of 5, were related with contemporaneous. In this is a version of the log n log s diagram for these events, and they identify that they have a relation between the number of events and the fluency, like a power law to the -1. However, we have to take into account that some of these events, or the majority of these events, are not extragalactic objects. In this new era of the modern X-ray missions like SWIFT, Chandra, or XMM, additional events have been identified in the archive data of these 3 telescopes. So I will explain a little bit about 3 of the most important events that we identified mining data of XMM, essentially Chandra. Sorry. The first one, it is called XRT 000519. The numbers that you have in here after XRT means the day, month, and year when this event was detected. This first event was identified by Juncker et al. In 2013. And here you have the light year of this event detected by Chandra. it is really bright. You can see a main peak, and also a couple of precursors events. And if we make a zoom in this main peak, we have a double peak structure. These events occur in the outskirts of the galaxy M86 at a distance of 16 megaparsecs. And so the first idea was, okay, maybe this transient was associated with this galaxy, which means that the peak luminosity of the event is in the order of 10 to the 42 ergs per second, which means a Eddington mass in the order of 10 to the 4 solar masses. So this association with M86 suggests that eventually this source could be related with an intermassive black hole because of the Eddington mass. However, recent observation of the field of these transients, using GTC, and here you have different images in J, R, and Y. You can see an extended object in here that could be related with the host galaxy of this event. The magnitude of this event is in the order of 25. And unfortunately, it was not possible to obtain a spectrum of this source to constrain well the distance that it is. So we don't understand well what is the real nature of this transient because we don't identify the real distance of the host galaxy. The other one, it is called XRT 141001, or also CDFS-XT1. This source was identified by Chandra in the Chandra deep field south. Yeah. So in here you have the likelihood of these transients. You can see that the flux increase quickly in the order of 100 seconds and then decreased like a power law to the 10 to the -1. The total duration of this event was around 5 kiloseconds. Trying to identify a potential host candidate of this event using HST data, BMOS, or FORCE2, was possible to identify the host galaxy. And we know that the photometric ratio of this galaxy is between 2.7 and 2.8, which means that the luminosity peak of this event is around 10 to the 47 ergs per second. And this event is particularly interesting because the field of the source was observed randomly by the BMOS instrument just 80 minutes after the S-ray trigger. That you can see here, an image of the BMOS observation. And unfortunately, we have just upper limits of a potential optical counterpart of this event. It is unclear which is the progenitor of these events. We have several candidates, intermassive black holes, TDEs, off-axis GRBs, or maybe a binary neutron star magnetar. And the last one, event that is called XRT 150322, was also identified in the Chandra deep field south. And here you have the likelihood of the event. This event has a particular likelihood with a plateau with a duration in the order of 2000 seconds, and then a power law decay like a time to the -2. And also, for this event, it was possible to identify a softening in the spectra that you can see here in the bottom panel of this figure for this event. This event also was possible to identify the host galaxy that you can see here. Yeah, we have a spectroscopy redshift of this galaxy, 3.5, which means a luminosity peak of 5 times 10 to the 46 ergs per second. So the association with or the interpretation of this event are related with the shape of the likelihood. We have this plateau and power law decay in the likelihood. We suggest that match well with what we expect for a likelihood of a rapid spinning magnetar, which follow this equation that you have in here. So the likelihood that you have in here, and also the distances, and with that, the luminosity of the source suggests that it's probably association with the magnetar remnant after the merger of two neutron stars. In the last year, several efforts have been done to identify and characterize transients, and particularly people start to analyze and meaning transients that are hidden in the Chandra data. And in Chandra was identified 22 fast X-ray transients, analyzing practically 2 decades observations, and was possible to classify these extragalactic transients in two different groups. 5 events were associated with nervy galaxies at a distance less than 100 megaparsecs. That is called the local fast X-ray transients, with luminosity peaks in the order of 10 to the 39, 10 to the 40 Earth per second. And also 17 fast X-ray transients were located with distant galaxies at a distance beyond 100 megaparsecs. And at least until now, for 7 of them, was possible to derive photometric and spectroscopy redshift in the range between 0.7 and 3.5, which mean a luminosity peak of 10 to the 44, 10 to the 47 Earth per second, which mean that in terms of luminosity, we have two kinds of groups of extragalactic fast X-ray transients, which mean that we have different origins related with both groups until now. So the current status of the X-ray emissions is the next one. Until now, XMM and Chandra particularly, they were not designed to give immediately alerts to eventually follow up fast X-ray transients using optical and near facilities. So until now, we don't understand or we have not detected the optical and near counterparts of fast X-ray transients, and that is a problem because without counterparts, it is really difficult to classify them, understand their nature. So we expect at this point that the extragalactic fast X-ray transients, we have subpopulations of them. However, we don't understand their progenitors. Additionally, the events that we identified until now, we don't have enough counts to make a detailed analysis of their lightyears and also their spectra, and also, of course, the evolution of the spectra. These different properties give us more ideas about the nature of these transients. Additionally, until now, we don't have triggers to alert events to try to follow up and eventually identify. The telescopes like Eurosita, they don't have fast alerts until now, and eventually when Nested Probe will be in full operation in June of this year, we expect to have really quickly alerts in the order of hours after the trigger or less than 1 hour to eventually follow up and obtain photometry spectra and try to classify them. And additionally, the current missions does not permit to identify robustly the host galaxy of these events. And this is a key point that eventually we have to solve. Okay, Axis mission, or the feature of Axis mission, will be permit us to increase our knowledge about extragalactic fast X-ray transients due to two important features of the events. The first one is the high resolution that it has. The BCF is in the order of 1 arcsecond, but is stable in all the field of view of the instrument. If you compare with Chandra that you have in here, so the proof it's a lot of, and this is really important because this will permit us to don't have these confusion problems with other X-ray sources, and additionally identify robustly the host galaxy of them. And the other key feature of Axis is the sensitivity that we have. The sensitivity of Axis and the effective area, it is higher than Chandra, how you can see in this plot, which permit us to have more counts and eventually give better analysis of them. So in the next slide, I will explain it a little bit about how Axis could be improved our knowledge of the extragalactic fast X-ray transients. The first one is the number of fast X-ray transients that we expect with Axis. So in here, we have a log S, log N, log S plot. This CN line that you have in here are the extrapolation of the log N, log S plot that I showed you with the old X-ray emissions. And this red line that you have in here is the new extrapolation that we derive using Chandra extragalactic fast X-ray transients. So consider this extrapolation of new data that we consider. We expect that with Axis, we'll discover around 50 fast X-ray transients per year, which means that the number of events will be increased by a factor of 13 regarding the current sample that we understand that we have more. This additional fast X-ray transient that we expect to identify and also consider the sensitivity of axis will permit us to have a better photon statistics, which means that we have more robust detections than the current missions that we have now. Regarding with the spectrum, so we expect to, with axis, we have more counts, and with that we have we can analyze better the spectra and the evolution of the spectra of events that we expect to identify. In here, for instance, this is the spectra of Chandra of one of the event, one transient, XRT000519. So we have a total number of counts around 3,000 counts with a flux of 10 to the minus 12. So to have an idea of how the number of counts will increase, we develop some axis simulations, consider the different particularities and calibration of axis, and we expect that for the same flux obtained a number of counts higher than by a factor of 2.5 regarding with the Chandra detection. This will permit us to make a more detailed analysis of the event that we have in here. Indeed, using axis, we expect to identify an event like this one until a flux of 5 times 10 to the minus 15 in flux, which meet a number of counts in the order of 40 counts, which, okay, 40 counts is not enough to make a detailed analysis in the spectra. However, give us an idea about robust detection and some shallow spectral analysis of them. Why this is important? Because if we have more counts, we can analyze in detail the spectral evolution. For instance, for this transient detected by XMM by Lindenthal in 2018, this event was located at a redshift of 0.05 in the outskirts of this galaxy. This is the bright galaxy, and here we have a potential globular cluster related with this galaxy, and it was possible to detect during 5,000 days how the spectra evolves with Chandra and XMM that you have here in the bottom panels. And it is clear that we have an evolution in the spectrum. And at later epoch, it is clear that we have an additional component, for instance, at high energy, that the authors, for instance, say that, okay, it's possible related with the corona emission of a possible accretion disk, because this event maybe are related with an intermassive black hole, which disrupt white dwarf star. So this is the interpretation. So the idea is, with more photons, eventually we can analyze better how the spectra change and how the spectra evolves, and with that we can make a better interpretation of the events. The other important key point is the light curve. The light curves. With more counts, we can construct better, and we can detect, and with the sensitivity on axis, we can detect this light curve several seconds, hours after the X-ray trigger. Yeah, in here, you have the XT2, some XT2 simulations consider the axis features. The black points are the Chandra detection that we have now, and the color lines are the axis simulation consider different peak flux. And here you have the different peak flux that we are considering. And the inside histograms are the number of counts that we have with these simulations. So in the original detection of this event with Chandra, we have around 100 counts. At the same peak flux, 10 to the minus 12, we expect an improvement in the number of counts. And with that, we can constrain better the light curve and observe the light curve and also 1 order of magnitude in times regarding to Chandra. And this is really important, because if we observe and construct well the light curve of these events, we can say different things related with the progenitor of this transient. As in the previous slides, I explained that XT2, XT1, and XT2 could be related with potentially proto-magnetar remnants formed after the binary neutron star emergence. Here you have the light curves in luminosity units and a comparison with other transients like short GRBs, the purple lines, long GRBs, the gray lines. This event, the black line, that is one event detected by Swift, that potentially related with a TDE, and also the supernovae 2080, a potential SBO. And it is clear that the likelihood of these events are different. In the case of X2, we have a plateau and a polar decay, and the other one, in X1, we have a fast rise and a potential overload. So the likelihood of these events give us an interpretation if we compare with this proto-magnetar model. What happened in the proto-magnetar model? So the model suggests that eventually when we have this proto-magnetar model, after the merger of two neutron stars, we have a magnetar and also ejecta material, which is reaching neutrons, and it's moving outside the location of the merger. And eventually, if depends of the duration that we are observing, we can obtain different likelihoods of the magnetar. If we are observing in a view angle direction, when we don't have the material, eventually we are observing directly the magnetar, and we expect a plateau and a power law decay. And in the case that we are in a direction when the observer is between the magnetar, if we have ejecta material which is between the magnetar and the observer, eventually this ejecta material could be absorbed part of the X-ray emission, and we can see and we expect a likelihood that in the way that we can see in here. So if you compare these two likelihoods with XT1 and XT2, maybe we can interpret it that both emissions, both transients have the same origins. However, the only difference in the likelihood are related with the direction, the view angle essentially. So with axis, we expect to observe beyond 10 to the 4 seconds these events by the high sensitivity that we expect with axis, and eventually we are able to relate the clue progenitor of the fast X-ray transients. The other one is the host galaxy identification. This is really important. The feature of axis, which has an excellent resolution of 1 arc seconds, will permit us to locate the host galaxy of the transients. And this is really important because depends of the host galaxy of the events, we can say if the source are related with different channel formations. For instance, in here we have a cartoon that more or less explains that. Eventually, in here we have the position of the transient, the yellow star, and in here the UV and infrared imaging of a potential host galaxy. So if we associate this transient with this UV bright host galaxy, eventually we can say that, okay, the transient are related with a young stellar population. So the best scenario that could be this transient could be a short breakout, or eventually something related with a long gamma ray burst. And in the other cases, if we consider an event when the host galaxy is bright in infrared, we suggest that the host galaxy has all stellar populations. We can suspect that the progenitor of these transients could be a white dwarf intermassive black hole tidal distribution event. And additionally, this high spatial resolution of axis will permit us to also identify the host galaxy and also the offset that exists between the transient position of the host galaxy. And the offset is really important because the offset gives us an idea, again, about the possible progenitor of the event. If, for instance, the transient is located at height of offsets, we can speculate that the progenitor of this event could be a binary neutron star merger when the offset is explained by the peak velocity once the neutron stars were formed, or maybe intermassive black hole tidal distribution events related with a globular cluster of this galaxy. In here, you have the cumulative distribution of the physical offset of the transient, and it is clear that the offset it is different between different kind of transients. It's not the same corcular supernovae or non-GRBs that you have in here, regarding with short gamma ray burst. So the offsets and the host identification gives you a better idea about the host galaxy, the origin of the transients. And additionally, we can identify the different in the parameter space of the host galaxy properties, like stellar mass and star formation rate that you have in this plot, we can compare with other kind of transients like supernovae 1A, core collapse supernovae, GRBs, data distribution events, and look if they exist some relation between the host galaxy phase X-ray transients and eventually other kind of transients. And here the different markers are different transients, and it is clear that all these events were detected by Chandra and XMM, they are located or we can associate it with a star-forming main sequence galaxy. All of them are above the galaxy main sequence, which in this case is the CN line. And also this gives you an idea about the potential progenitor of these events. This is one thing that AXIS will be permitted us in the future. And finally, I will talk about the contemporaneous content of the transients, and this is really important. As you explained you before, until now, just one event was identified a potential optical and near-infrared counterpart. Just in one case, in this XT1, CDFS XT1, was possible to observe the field of the event 80 minutes after the X-ray trigger. However, we have just upper limits. So eventually, if AXIS will have an onboard alert, which permitted eventually observed events with other multi-wavelength facilities, will permit us to classify better what kind of extragalactic transient that we have. In here, for instance, in this panel, we have the upper limits of the detections that we have in optical bands, essentially, of XT1. And here we have the point that we detect 80 minutes after the trigger, and in here we have different merger nova models. What is a merger nova? A merger nova is a kilonova when we consider that proton magnets are also enhance the emission of the kilonova. So all these events, all these emissions that we expect, they occur really fast, less than one day. So we have to eventually, with AXIS, a tool which permit us to have immediately alerts and eventually observe these events. Take, for instance, spectra of the potential progenitor of these events, like binary neutron stars or tidal distribution events involving quite dwarf and intermassive black holes. And also, this will be permit us to answer some questions that we don't understand well until now. For instance, one of these is the cosmic volumetric rate. With the few detections that we have now, we have some not well constrained in the density rate of these events. And here we have the rate of this phase X-ray transient that we identified by Chandra, this horizontal gray band, and a comparison with the cosmic volumetric rate of massive star, major compact object, or TDEs. And it is clear that this rate match with different kind of objects in different redshifts. We suggest that the sources that we have a mix of origins, and also that we need additional detections to constrain better this cosmic volumetric rate. Just finally, like some conclusions, okay, we understand that Chandra and XMM that they were not designed to give quickly alerts to eventually observe potential phase X-ray transient with other facilities, and it is one thing that eventually AXIS will be permit us. Also, AXIS has unique capabilities in terms of spatial resolution, effective area, and sensitivity, which will permit us to increase the number of phase X-ray transients that we have now. Also, have a better constraint in the timing and spectral properties. Spectral evolution will eventually permit us to classify better events. And finally, also will be possible to have a host identification, and it is really important to determine the distances and with that energetics, and also understand better this enigmatic new class of astronomical objects. Thank you so much. Thank you for your attention.
Great. Yeah, that was a really interesting talk. So maybe I'll ask the first question and other people can think a little bit. So, you know, we sort of have historical numbers from Rosat and other missions. And then when you want to go to deeper fluxes, you really need something like Chandra or XMM. But I would assume that like most of the archival data that you've searched is probably in like deep fields. So how do you think that kind of bias affects, like the types of sources you found? I mean, I guess you found there's also this class of nearby systems. So I guess those are maybe just because people are continually observing those sources, maybe for supernova or other things like that. But how do you think that bias sort of affects the types of sources that are found, and how much more can we get out of the archives? Like, Chandra keeps kind of observing, and there's a lot of different random pointed observations. Like, is there a lot more, or are we kind of at the limits in terms of finding these ones? Obviously, we want, it'll have happened a while ago. So,
yeah, in the case of Chandra, if you remember, we identified two events in the Chandra the field set, which is it's one of the fields that Chandra visits several times, and also other two events were identified in a field that it's a field that I understand that Chandra used like a calibrations. So, and we have four events that was identified in deep in deep fields. So yeah, of course, there exists a bias related with that with the deep fields that we are at least with Chandra data that we have. So yeah, that is one problem of Chandra. So Chandra pointing randomly in the sky. So the chances that eventually try to identify one object is it is low. However, our current rates that we identify means that in all the sky we have in the order of 10 to the 6 fast X-ray transients in all the sky. So with that rates, we can conclude that they are common sources that we expect in the sky. However, we expect to eventually improve our detections. We expect with instant proof, we have in the order of 15 fast X-ray transients per year. And that will give us more chances to understand better these interesting sources. Indeed, last week or 2 weeks ago, the first instant proof detection was reported, and now this is in a commission phase. So it is really interesting. What are the next related with transits?
great. Rick, you want to ask a question?
Yes, Jonathan. Did you consider TDEs with objects other than white dwarfs?
Okay, if we consider the traditional TDEs, supermassive black holes and main sequence star, we don't expect a peak in the X-ray emission, in the soft X-ray emission, like the fast X-ray transients that we try to identify, because one of the characteristics of this fast X-ray transient is the time scales in the order of minutes and hours. So the time scales that could be covered in terms of tidal distribution events just are the intermassive black holes. So of course, the supermassive main sequence star TDEs, they have a different time scales in the order of months. So yeah, the science it's quite different regarding with the fast X-ray transient that we are interested in our research essentially. So we have two different kind of TDEs essentially. The time scales are different.
Thank you.
Sure.
Yeah, there could be beaming effects. The TDEs with jets and the beaming could give a faster transient time scale that might just rise up above the peak. So there is that chance, but we're still uncertain about what the radio jets are in TDEs and how they kind of how they're fueled.
In here, this one, Swift 1644 plus 57, which is the black one here, the best interpretation that in the literature related with the transient is supermassive black hole jetted TDE. However, as you can see here, the light curve is really, we have flaring events in the light curve, so it is, and the time scale is different if you compare with the fastest transient that we have in here. So we have a hole between them.
So I have one more question just about the spectra. I mean, I know a lot of these you're not getting a huge number of counts, but is there a lot of variation in terms of how soft and hard they are? Do some show significant obscuration?
Yeah, at least for the events that we detect until now in here, for instance, XT2, sorry, it is really clear that we have in here a softening in the spectrum, and it's one of the few events that show this this softening, and the softening gives us an idea about maybe we have event that it's cooling, maybe in the case of, for instance, SBOs, for instance. However, the interpretation of this evolution in the spectra, it's unclear. Indeed, for this event particularly, when the author said, okay, maybe it's related with a spinning magnetar, this softening is not completely understood, to be honest. And it's not part of the interpretation because it's a little tricky how this evolution are related with, for instance, with a magnetar model, something like that. But it's one thing that eventually we have other events at this point, but it's an unanswered question until now. But
Jonathan,
really
do you have a picture of the hardness ratio or the spectral index that you measured for the sample? Do you have in the backup slides? No.
I don't have it. I don't have it.
Could the softening just be due to material clearing out of the way and there being less low energy absorption?
Yeah, it is possible. However, I am not sure how that interpretation could be related with, at least with the interpretation that we have, that currently we have for this event particularly. And how this could be fit with the other properties that we have. The offset, for instance, with the host galaxy or other ones. So it's a little tricky how the spectra fit with the other properties of the transient.
Yeah, just to sort of come back to Mike's point, we only have 22 objects. They have a variety of properties at the moment. A variety of redshifts, a variety of hosts or no hosts, a variety of X-ray properties in terms of their typical X-ray spectral shape. We have some that are soft, some that are relatively hard. We have different light curves, and so it's probably a very heterogeneous population. There's probably some binary neutron star mergers here. There's probably some off-axis GRBs. There's probably some kind of frustrated jet GRBs, like very low luminosity things. There's probably some TDEs of various ilk. There are not too many shock breakouts, but there might be one or two in here. And so, yeah, so building up larger statistics and better statistics in terms of the X-ray counts can help to flesh out which portions of parameter space are really being filled by this population.
Yeah, I mean, one thing I was sort of interested in is, I mean, I understand probably the 50 that you were, or the amount that Axis will detect, you're giving kind of a conservative number, but I was just thinking that if you actually had, onboard software and you were really tracing, that you'd probably detect a lot more fast X-ray transients, just because, the method now seems to be, go to these fairly well-studied fields. And I guess the other point.
The sample that Jonathan amassed was basically taking the entire archive above a certain galactic latitude, like 10, and then removing all the observations with less than 8 kiloseconds, because we can't really, we're not sensitive to anything at 10 kiloseconds. Like if our event is 10 kiloseconds long, we can't really distinguish it from a variable AGN. And so, he analyzed 260 megaseconds of data.
Oh, okay.
So it's a significant fraction of the extragalactic archive.
Right. Oh, okay. Yeah, I didn't realize that. I guess the other question is, will, like the large Euclid sky survey and some of the other things that are coming online really help in terms of getting counterparts? Or is that not as much of an issue?
Sorry, what do you refer with the next surveys? Sorry.
Well, I was wondering how many of these, sources do you not know where the counterpart is, because you just don't have HST imaging or whatever. And the fact that Euclid's going to survey, 17,000 at fairly high spatial resolution, if that'll help a lot, or, because you can really focus on these sources, you can just get deep images or JWST or whatever, if that matters.
Okay, until now, some depends. Okay, it depends on how close to us are regarding to us. So eventually, yeah, it is possible to observe at least the closest one. So with intermediate facilities that we have now, so that is not a problem. So eventually, we can expect to identify these events, the counterparts. But the only problem with the surveys that you mentioned is, if I understand what your question, we have to expect two different matches, that the X-ray telescope that we have now are pointing in the same direction that the deep surveys are also observing. So
right. Yeah. That's
the problem.
Yeah. I was just thinking with LSST, or Euclid observing large patches of the sky. But
sure.
I guess you really need something that is very contemporaneous, within a few minutes to get the optical IR counterpart, because obviously it's very faint. So anyway, yeah. I think
the population that access will detect the largest will be relatively faint. They won't be so nearby, although access will detect some because it's just a wider field of view than Chandra.
Right.
So just to translate Mike's question, so Euclid is going to observe to near infrared depth of 23rd magnitude or 24th magnitude over 17,000 square degrees of the sky, so roughly 1/3 of the sky, and all the extragalactic sky. LSST at the end of 10 years will have imaging to, typically 26th magnitude over much of the same area. And so, right, if you have that depth, right, that's kind of comparable to the depth we have now in HST fields. And so how would that do in terms of constraining the host galaxies? And then thinking about, if you had a facility that was observing the sky every few days, like LSST, to 24th and a half magnitude, how would that do towards characterizing the potential, contemporaneous counterparts?
No, okay, yeah, with that limit, yeah, it's possible to eventually characterize the counterparts, but
the host.
at least the host, yes, of course, the host is with a 26 in magnitude. This is the limit of the host magnitude that we identified with the sample that we have at this point. So yeah, at least in some colors, yeah, spectroscopy is not possible. But yeah, in terms of colors, yes, it's enough maybe to make a crude interpretation, or a crude distance, which is the most important thing that we need for these events. for the energetics. So yeah, that would open several options to understand better the sample. Yeah.
But
Great.
the contemporaneous counterparts would still need immediate follow-up.
Right,
Yeah,
right.
that's the
Yeah.
problem. Mhm.
Yeah, yeah. I mean, there'll be a lot of different spectral surveys, so hopefully that will be, yeah. But
But
yeah,
at this point, we have experience with the gravitational wave counterparts also. More or less, it's the same problem.
right. Yeah,
yeah.
yeah. So we should get a lot better. Yeah, yeah. Great. Well, yeah, thank you so much for that detailed talk. It was great to learn more about this. And yeah, we'll catch up in a month for the next seminar. All right, take care. Good to see you all.
Thank you, Mike.